Well, now we're going to look at this optical sampling a bit closer. I'm going to introduce you to Harry. Now, who was Harry? Well, he's a man a little older than I am, and he was born way back. And in 1928, he wrote a famous mathematical paper which haunts us to this day, and we can't get away from it. He said, if you sample optically with a sensor, if you sample electrically, digitally or whatever, you are stuck with a fundamental rule. Let's say I have a CCD that's looking at an image and it's photosampling that with lots of what we call the photosites or imaging pixels. You now have all those samples in that sensor. You have to reconstruct the signal to get something useful, like the video signal. In that reconstruction, he is saying your sampling of frequency of those sites must be twice the highest detail that's in the image of interest to you. Otherwise, you're going to get an interference. We call it aliasing, moire. It's that nasty thing that can go on in a picture. I'm sure you've all seen it. There's all sorts of adjectives to describe it. But it applies to the sensor that's doing optical sampling, and it applies again to the digitization process that's doing digital sampling. So Harry hits you twice in any camera. What he said was, if I've n samples, let's say across a line or n vertically, I can only resolve n over 2. So 1920 says I can unambiguously resolve half of that, 960 line pairs without any interference. But if something comes in from the lens that has a frequency higher than 960, it's going to generate a problem. And I'll try and show you that in a moment. Now, we generally don't talk about line pairs per picture width in the video world. We like to have equality between horizontal and vertical, so we transform that 960 by the inverse of the aspect ratio, and that says we can resolve, with 1920 samples, 540 line pairs per picture height across the picture on one line. Showing it graphically, it says if I've got an imager with, let's say, millions of these little photosites, and if the photosites are large and they abut one another, you get a curve like this. Comes to a 0 at the optical sampling frequency, and Nyquist is half of that, and it says this is the good stuff, this is the bad stuff in here. Every camera manufacturer on the planet has to contend with this. It's fundamental to the design criteria, is how do I get this curve to be as high as possible, because that's my resolution, and minimize this interference from here. And we'll talk a little bit about that. Now, most sensors, however, do not abut one another. These are the photosites. They have spaces between them because there's tiny little electronics in here. You get a fill factor. When you get that, the curve lifts, believe it or not. As that space becomes bigger, that curve lifts. That's great because it gives us more resolution, but it's bad because it gives us a lot more energy to generate the interference signal. The other dilemma that the camera manufacturer has to wrestle with. As they design a sensor, they have to consider this factor. They don't tell you. Nobody publishes their fill factor, but it has a bearing on what you ultimately get. Here's the problem. I talked about aliasing. Let's say the lens projects onto the sensor a very high frequency detail from the scene. I'm simulating it with these line pairs per here. If it's very high and it's near this carrier, it will then generate a low frequency, spurious signal, very low down. If it's here, it'll generate it here. If it's here, it'll generate it here. That's aliasing. And once you have that, and you've done nothing about controlling it, and it climbs into your signal, you cannot remove it. It's indelible. That's the challenge, is to confront that. So good area, bad area. This is your resolution. This is your nasties. You've got to control. How do they control it? They pre-filter. Here's the sensor doing the sampling. You put an optical low-pass filter in front of it, designed to have a certain characteristic, horizontal and vertical, to try and keep your in-band resolution up and get that aliasing down as far as you can. There's no perfect way of doing that. You end up with a trade-off. All camera manufacturers have their own criteria for this, not published by anybody. So two variables are never published: the fill factor of the sensor and the optical low-pass filter. They will make references to things that they do. So you have an imaging clock in the front section that sometimes is published that is talking about the readout mechanism, or your CCD or your CMOS. Then you go over digitize, where you have a digital clock. Now, if the photosite number is the same as the digital sample number, these clocks would have the same frequency. But in many cameras and camcorders, they are different for the reasons that I've stated. And you have to, because of this sampling, you have to have an electronic pre-filter. So all cameras will have an optical pre-filter and a digital pre-filter. By the way, the lens that hangs on the front of the camera has its own shape in terms of response. So it is another pre-filter that has to be taken into account. Now, linking optical sampling and digital sampling. I'm doing this as simply as I can. It's a little techy, but maybe it'll get a point across. We're in the camera. We're in the sensor. The sensor's looking at the image from the lens. It's sampling it. So it's got a sample frequency and it's got a Nyquist, an optical Nyquist. And this is what's good, this is what's bad. This is what the sensor's response is. The camera designer puts in an optical pre-filter. I've just sketched an arbitrary one there. They all have their own design criteria for this filter. And what it does, it transforms that blue into that green, and we've kept most of that, but we've had to trade off some resolution in order to get that aliasing way down. That's the analog coming out of the sensor. That is then sent over to the digital section. The digital section has a digital sampling frequency and a digital Nyquist. May or may not be the same frequencies. I'm showing them different. Now you have to put a pre-filter here to pre-filter this analog signal so you don't offend this limit. And you will get then, this will enter the A to D converter. It will be pre-filtered, and now you digitize that. And Nyquist is happy over here. And what you actually get coming out of the camera is the digitized signal that I'm showing red. All camera manufacturers will then put in near the output of the camera a final filter. In the case of the high definition standards, the shape of that filter is prescribed by the SMPTE. It's built into the production standard. It's a 30 megahertz filter for those of you who are interested. And it's deliberately below Nyquist, keeps you well away from Nyquist. So what you end up with is this red curve that gets lopped off here by this digital filter. Now, here's the bottom line. This is the digital handover coming out of the camera, or in the camcorder, that's what would be handed over to the recording section of the camcorder. The resolution characteristic, this part here, has been totally determined by the camera section, the photosensor. If the digital folks have done their job right, they don't touch that. They don't mess with that. And that means they got to have a good high digital frequency. What the digital does do is it gives you that lop off and determines what we call the limiting resolution of the camera. And you'll sometimes see in the brochures, camera limiting resolution, 1,000 TV lines per picture height, and that's that 1,000 TV lines would be somewhere there. But you can see what I'm saying, that the analog has been shipped into a digital container, and that hands it out. And this digital container might be 1920 by 1080, might be 1280 by 720, or in the case of some of the digital cinema cameras, those digital numbers that they use for their digital 2K and 4K. And this is where you would measure at the output of the camera the resolution, the actual resolution.